Hello, welcome to my next lesson here. Again, rough attempts, just trying to get started with all this. Uh, what we have here is a lesson on the real number system and the different types of real numbers. In this lesson, we want to be able to compare and order real numbers, estimate irrational numbers, and of course, classify the different types of real numbers using words like natural, integer, rational, irrational. This will be our sort of graphic organizer for the entire lesson. If you're participating as part of my class, of course, you should have a printout of this with the boxes ready to fill in. We'll be doing a version of this in the Paint program since I can't easily write on it in the PowerPoint right now. Before we get started with this lesson, I'm going to use the word set a lot, and I want to make sure you understand what that means in math. A set is a group or collection, but we can consider it as a whole, even though it's made up of all these individual parts. Think about a forest is a bunch of trees, or your class is a bunch of individual students. But it's sometimes easier to talk about the forest as a whole or the class as a whole than it is to talk about it as a bunch of individuals. And we'll have a little bit more detailed lesson on sets in the near future. Kind of review from the previous lesson. Of course, we talked about natural numbers a lot in that lesson and different types of natural numbers. I want to point out that most humans, of course, part of learning to count is to count on your fingers. Most people have 10 fingers, and so our system of math is more than likely this base 10 number system based on our anatomy. We have 10 fingers. Worth mentioning, though, is there were some cultures and civilizations that used other base systems. For example, base 60 in ancient Mesopotamia, or base 20 amongst the Mayans. We actually still have a little bit of this base 60 system left over, thousands of years later. This is why there are 60 minutes in an hour, or 60 seconds in a minute, and it's also why there are 360 degrees in a circle. So natural numbers, the numbers we know and love. Well, if we're going to be thinking of them as sets, then to include them and think about them all at once, we use these braces to enclose the set, and then we would use the ellipsis, the dot, 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 to show that it does keep going. Some people might be asking, well, what about zero? In elementary school or middle school, you might have heard about the whole numbers, and that included zero in addition to the natural numbers. Whole as in like a hole in the ground. If you forget the W, kind of looks like a zero. But for purposes of this class, when we need zero to be a natural number, we'll just make it a natural number, but most of the time we'll be looking at natural numbers as these numbers. And we won't worry about too much about whole. We'll immediately skip from natural numbers to integers. But before we go on to integers, worth mentioning is that mathematicians are notoriously lazy. We like to invent all kinds of symbols and shortcuts for things. And so when you're talking about the set of natural numbers, you'll often just refer to it as a capital letter N. Integers come from the idea, again, of owing or debt. And so this set, you would actually have an ellipsis on each end because it does go off to both the left and right, so to speak. And most people think about integers, they probably think about marking off numbers on the number line. A name for the integers as a set is actually going to be Z, which comes from the German word for number. We're not going to use I because there are a couple different number words related to I, and we don't want it to be potentially confusing. Alright, so let's talk a little bit about where the real number line comes from. There are infinitely many real numbers. There are infinitely many points on a line. Hopefully I can get you to agree with both of those. And then at that point, the idea is, well, let's create a one-to-one correspondence. And a one-to-one correspondence is getting back to that idea that even if you can't count, you can decide you have the same number of fingers on each hand because you can match them up. And so even though there are infinitely many real numbers, there are infinitely many points. Infinity is a really big, hard, tricky concept. What we do is we start pairing up numbers and points on the line to create what's called the real number line. And this R right here, by the way, the R is going to be like the symbol for real numbers. And this is basically a metaphor like you would see in an English class, where we're taking the idea that numbers are points on a line. Let me move that out of the way. I'm sorry. Alright, so a couple things about the number line you probably already know and don't need to write down. But this gets us into how the number line is actually made. You pick some arbitrary point on the line and you pair it up with 0. And you go to some arbitrary point to the right of that point and you call it 1. And then you've got a scale. And once you have a scale, you can find 2, 3, 4, or you can go find negatives. -1, -2, -3, -4, -5. It happens to be labeled. And so the idea is you can get all the integers just from picking a 0, picking a 1. That gets you a scale, and then next thing you know, you've done the tick marks. And of course, if you're to the right of the origin, your number name is going to be a positive number, and if you're to the left, it's going to be negative. And so think of this idea as we're naming each of these points on this line with a number. Somewhere right in here is a point whose number name is going to be -√3. But that whole number name business, you get tired of saying that. And so that ends up being what we call a coordinate. And so here is a point whose coordinate is 1/2. That's the name of that point or location in terms of a number. Okay, a little bit more about just sort of this idea of putting numbers into order along that line. Let's suppose we've got two numbers that are distinct real numbers. There are basically two options. Either A is less than B or A is greater than B. And I've missed italicizing these, but we'll be alright. Well, of course you probably remember the inequality here, A is less than B. The one that can be bent into an L is less than, in case you've forgotten. And you probably remember that the geometric version of less than is that A is to the left. What you might not have known is that in terms of arithmetic, if you do the subtraction A minus B, you'll always get a negative if A is less than B, which makes sense when you hear it, but it's not necessarily the way you were taught to think about inequality. Similar, A is greater than B, here's the inequality, A is greater than B. You're probably not shocked too much that instead of being to the left, we're looking at to the right. Instead of being negative, we're looking at positive. This is the one where students start to seem to have trouble, because I don't think you've worked a lot with these numbers, but maybe you haven't been forced to learn this word, or the phrase here, the rational numbers. Rational numbers are real numbers that can be written as a ratio of integers. And so obviously a ratio of integers is just a fancy way of saying fraction. And then the other thing that you get in here is that you get integers for free, basically. Talk about that in a second, but the basic idea is that the denominator would be 1 for any integer. You also get decimals that terminate or repeat in a pattern. And the symbol for rational numbers is Q from quotient. And I have a couple examples here of rational numbers. Here's a decimal that terminates or stops. This is how we usually will write a decimal that repeats. So it's 0.222222, and the bar is just used to show that it repeats. And then here's a couple of nice little fractions. I want to pause there for a second and look at the word rational and point out to you that ratio is hiding inside that word. The word tells you that the definition is going to be about ratios. Okay, well, what's a ratio? We said that what's kind of the idea there is that it's a fancy word for fraction. So here we look at fraction. Oops, it's supposed to be red. And you see that ratio is actually also hiding in the word fraction. And even better, the word that's kind of most related to fraction that you might actually have heard and on a regular basis is fracture. And you probably know that a fracture is just a fancy word for broken. And so what we have is that the rational numbers are numbers that have been broken up into smaller pieces, fractions and decimals. So any integer is going to be rational because it could have an understood denominator of 1. And getting back to sort of that idea of the number line for a second, we like the rational numbers because it not only gets us the tick marks, like the integers, but you can also get between the numbers, like 3.5, for example. And of course, you find the average between two numbers, you'll definitely be, between two numbers. And so what happens is between any two numbers, 1 and 3. Well, between those with integers, there's only 2. But for rational numbers, there are actually infinitely many numbers between 1 and 3. There's 2, but also 2.5, and 1.7, and 1.003. I mean, there are just infinitely many numbers that you could find and name between 1 and 3, which we don't get that with the integers. With the integers, if you pick two numbers that are right next to each other, like 2 and 3, then there's not even anything between 2 and 3 as far as integers are concerned. What about irrational numbers? Well, the prefix IR tends to mean not. So just like irregular means not regular, irrational numbers are not rational. So they cannot be written as a ratio. They do not terminate. They do not repeat. In other words, when you look at an irrational number decimal expansion, it's going to go on forever and just look random. And so what you've probably been taught in the past is that pi or square root of 2 or some of these other square roots are irrational numbers. And so you might have even in middle school had contests where you know that pi is 3.14159, and it just keeps going beyond that forever with no real pattern. And you might have even had contests about, some teachers do, who can memorize the most digits of pi. So most of these irrational numbers we have to name with a symbol like pi or square root of 2, and then it's also nice to eventually kind of get down a rough estimate of these types of numbers. So I'm going to pause and kind of go to our graphic organizer here and start filling this thing out a little bit. And so what we have, of course, real easy, is naturals, 1, 2, 3, and so on. Integers is when you sort of throw in not only these numbers, but you've also got 0, and 1, and -2, -3, and so on. And then rational, you can't list. You can't list the rational numbers because between any two numbers, there's going to be a new rational number. So right now, we don't have any way of sort of approaching a list for these numbers, and so we would just talk about, the idea that it's some number compared to some other number, and so things like -1/2, 0.3 repeating, 5.27. And of course, it also includes any of the integers, any of the natural numbers. The idea here is these sets are like containers. And so if the integers contain the natural number container, not only do you have these sorts of numbers, but you also have anything inside of it. But there's, some extra stuff that make the naturals and the integers different. Well, again, there's going to be nothing in common here because you can think of these as the not rational numbers. The not rational numbers, and all we can really do right now is throw out some examples. One thing worth mentioning is that when I start writing down the examples of square roots that are irrational, why do I have to skip the square root of 4. And hopefully you can quickly go, well, wait a minute, the square root of 4 would be 2. And 2 is a pretty nice little natural number, and there's not supposed to be anything in common here. So it's not necessarily true that any square root's irrational, just the ones that don't simplify to something nice. And then what we have is that if you take all of this together, that's going to be what we call the real numbers. That gets us all the numbers on the number line. And again, our symbol for rational number, or excuse me, real numbers, is an R. Rational is going to be a Q. Integers is a Z, and natural is an N. And there is no nice symbol that I'm aware of for talking about irrational numbers quickly. We don't use that one because, again, you try to avoid I, because you've got integers, you've got irrational, and then you've got sort of a really big idea is there anything outside this box? And it turns out that the answer to that question is yes. And hopefully by the end of the year I will have shown you what exactly is lurking out here outside the box, so to speak. What's not a real number really mean? And so this was kind of what we were just looking at in that diagram. The real numbers is the both rational and irrational together. Every real number, every number on the number line is either rational or irrational. There's no new numbers involved. We'll just put two groups together. The symbol there is R. We care about these numbers because they make algebra work the way we expect it to, because it has all these nice properties that we'll look at in another lesson or two. And again, what does not a real number really mean? By the end of the year, I hope you understand that. So that's the vocabulary for this lesson. Let's look at some of the problems or example problems on the bottom of the page. Well, one of the things I want you to be able to do, is be able to estimate irrational numbers. And I don't want you to have to do anything on a calculator to be able to do this. So you look at this and I say, well, don't touch a calculator and try to estimate a value for the square root of 16. And maybe after a little bit of thinking, you remember that 4 squared is 16. Okay, so whatever this number is, it's more than 4, but not by much. So maybe 4.1. And then you'd have to check that on a calculator to see how close you were. Okay, well, what about the square root of 87? Well, you think about some square numbers, and maybe you remember, we did square numbers, of course, in our previous lesson, that 9 squared is 81, 10 squared is 100. So this number is between 9 and 10. I could have said that over here. I could have said this one's between 5 and 4. But it was just so close to 4 and went ahead. Now, where do you think this number is at in terms of 9 point what? If we had to throw one digit here as an estimate, 9 point what? Well, it's clearly 81's a lot closer to 87 than 100 is. These are 6 apart. These are 13 apart. And so, you know, this is 6 away and this is 13 away, then this piece right here is roughly twice the distance. And so this is basically about thirds. This is like a third, and another third, or a third and 2/3. And so my guess for this would be 0.3. if I had to guess, because 87 is about a third of the way between 81 and 100. And again, no calculator. Could I be a little off? Probably, but that's how you guess and estimate without the use of a calculator. By the way, I'm sorry that I am getting a little bit of a cold, so if I'm even more difficult to listen to than usual, I apologize. Alright, well, this one right here, square root of 24, again, it's kind of an easier one. It's just a little less than 5. And so my guess here might be 4.9. It might even be so close to 5 that if you round just one decimal place, it might even round to 5.0. Now for this one, square root of 42. Well, you stop and you think about squares, and then you hopefully come up with that 6 squared, 36, and that 7 squared is 49. Okay, so how's 42? Well, it's obviously between 6 and 7. Square root of 42 is between 6 and 7. So it's 6 point what? If we had to come up with a one decimal digit guess. If we had to go to the 10th place. Well, it's 6 away from 36, and it's 7 away from 49, which I find an interesting coincidence, that it's 6 away from 6 and 7 away from 7. And so to me, I'm going to say, well, that's about halfway then. And so my decimal estimate on this one would be 6.5. And again, I haven't even checked any of these on a calculator, but I know that I would be fairly close. And so if you want to check them, go for it. One of the other things we needed to do was classify numbers, and we want to be as precise as possible here. And so 0 for us is an integer. I know we had talked about that we were going to leave whole numbers out, and so some of you might say, well, is it a natural number? For purposes of this class, most of the time, we're going to think of it as being an integer. So what about 56/7? Well, you might be tempted to go rational because it's a fraction, but on Alex and things like that, they're going to be sneaky occasionally, and they're going to throw a fraction at you that maybe you don't immediately realize simplifies or reduces. And 7 times 8 being 56 is probably one of the multiplication facts that people are most likely to forget. So the most precise name for this number is actually 8. 8's a better name for this number, and so we should say that it's a natural number. Alright, what about the square root of -9? Well, the square root of 9 is 3. This is the square root of -9. And oh, wait a minute. If you remember, we talked about this just a little bit in that last class. We had talked about how the best answer here is not a real number. We cannot do the square root of a negative. Not a real number. And for right now, that's the best answer we can get. By the end of the year, maybe we'll be able to do a little better with that one. Alright, so here's another one with a square root. And it's got a fraction inside the square root. And kind of similar to the one above them, it is actually a fraction that will reduce. So we would need to reduce this fraction before we do anything else. And 16 goes into 48 3 times. So it's the square root of 3. Square root of 3 isn't going to simplify any more than that. So this is a irrational number. Alright, I'm going to pause if I can right there for one quick second. Okay, and I'm back. We have this one last example left to do where we need to figure out how to take this list of numbers, and we're going to sort it into order from least to greatest. And I didn't use this word in the directions, but it wouldn't be completely uncommon to see this just say sort into ascending order. Order from least to greatest. The numbers need to get bigger. And then after we get them sorted into order, we're also going to sort them again based on what kind of numbers they are. I'll try to do that pretty quickly. My strategy for this problem would be to first notice that there are only two negative numbers. So I'd go ahead and put those down first. And then I would mark in some way that I've used those two. And then 0 is in our list, so it would come next. And then start looking at the numbers that are less than 1. So 0.3 repeating, 3/4, 1/2. Well, you hopefully know that 1/2 is 0.5, and you hopefully know that 3/4 is 0.75. And so our smallest of the numbers we just mentioned would be the 0.3 repeating, then the 1/2, then the 3/4. And so we use that, and that, and then we're ready for 1. And that was probably the hard part for this particular list of numbers. Now we're ready to take out and make sure we get all these numbers that are greater than 1. We've got 2, 1.5, and square root of 2. Maybe you need to check a calculator, but I know that square root of 2 is about 1.4. It's actually 1.414. But I know that it's less than 1.5 or 1 5/10. And so the next number we would need is square root of 2, then 1.5, and then 2. So we use that one, and that one. So there's all of our numbers. That would be the complete list. Now let's try to sort them here. And I'll just use big N for natural numbers, since that's a way. Well, if you look through this list, only 1 and 2 are natural numbers. Okay, integers. Well, -2, -1, 0 is an integer, 1 and 2. The symbol for rational numbers is Q. Most of these numbers are going to be rational. So -2's rational, -1, 0, 0.3 repeating's a rational number because it's a repeating decimal. 1/2 is clearly a fraction, as is 3/4. So they're both rational. 1, square root of 2 is one of our standard examples for being irrational. So we need to skip it. 1.5 and 2. Okay, and then so the only number we're working with that's not rational is square root of 2. It's the only irrational number. Now, don't let this example fool you. Some of the reasons for why it's true are a little complicated, but if you were to just randomly pick a number off the number line, it's actually more likely to be irrational than rational. If you truly picked a random number off the number line, turns out there are more irrational numbers. They're just not as easy for humans to think about them, so we don't deal with them as much. And so it takes you a while to hear about irrational numbers, but then once you know them and understand them fairly well, you'll find that they are actually much more common than even the rational numbers. And so, people don't tend to like them very much, but most of the numbers on the number line are not nice numbers. They're these decimals that go on forever without repeating. I think that's it for us for today. I'll check real quick. It is indeed the end. I'll need to see if I can splice these two clips together. Thank you very much. See you next time. See you in class.